Assalamualaikum and salam sejahtera. Hi there everyone. Cikgu Zana is back. I hope all of you are doing fine, especially to all the beloved PRIU students out there. Today's video lesson is the continuation of the previous lesson, Integration Area of Region Part 1. So in Part 2, we will learn how to find the area of a region bounded by two curves. I hope that this lesson will be beneficial in helping all of you to do your revision. Okay, shall we start? Let's look how we can find the area of region bounded by two curves using integration. In the diagram, the curve y equal f of x and y equal g of x intersects at x equal a and x equal b. Thus, area A is obtained by finding the difference between area of B and area of C. That is, the area inside the outer curve minus the area inside the inner curve. Thus, the area of A can be obtained using the integral of f of x minus g of x from x equal a to x equal b. Consider the area of the shaded region given in the diagram. The two curves x equal f of y and x equal g of y intersects at y equal a and y equal b. The area A is the difference between area of B and area of C. In other words, the area inside the outer curve minus the area inside the inner curve. Thus, the area A is obtained by finding the integral of the function f of y minus g of y from y equal a to y equal b. Let's look at the first example. Sketch on the same coordinate axis the curves y equal x squared and y equal x multiplied by 4 minus x. Find the area of the region bounded by the curves. The first step is to find the point of intersection between the two curves. So at point of intersection, x squared is the same as x multiplied by 4 minus x. Simplifying, factorizing, x equals 0 or x equals 2. When x equals 0, y is 0. When x equals 2, y is 4. Therefore, the point of intersection are 0, 0 or 2, 4. Now, both curves are quadratic curves. The curve y equal x multiplied by 4 minus x has a maximum point 2, 4, while the curve y equal x squared has a minimum point 0, 0. So sketching the x-axis, the y-axis, the curve y equal x multiplied by 4 minus x with the maximum point 2, 4. Sketching the curve y equal x squared with the minimum point 0, 0. Thus, the area of the region bounded by the curves is given by the shaded region. Next, we find the area of the shaded region bounded by the two curves. The required area is the integral of the function x multiplied by 4 minus x from x equals 0 to x equals 2, which is the area inside the outer curve, minus the area inside the inner curve which is the integral of x squared from x equals 0 to x equals 2. Simplifying, integrating, we have 2x squared minus 2x to the power of 3 over 3. Substituting the upper limits, substituting the lower limits, we have 2 and 2 over 3 units squared. Example 2. We are given two curves with the equation y equal e to the power of x and y equal 1 plus 2e to the power of negative x. Find the coordinates of P, the point of intersection of the two curves. Calculate the area bounded by AB, the arcs AP and BP. At point P, e to the power of x is the same as 1 plus 2 multiplied by e to the power of negative x. Multiplying both sides of the equation by e to the power of x. Simplifying, we have e to the power of 2x minus e to the power of x minus 2 equal 0. Factorizing, since e to the power of x is always positive, e to the power of x cannot be negative 1. Therefore, e to the power of x is 2. Taking a ln on both sides, x is ln 2. When x is ln 2, y is 2. Thus, the coordinate of P is ln 2, 2. Looking at the shaded region, it is easier to integrate with respect to x instead of y, as the integration of the functions x equal ln y and x equal ln 2 over y minus 1 are more complicated. Thus, the area of the region is the integral of the function 1 plus 2e to the power of negative x minus e to the power of x, that is, the area inside the outer curve minus the area inside the inner curve. Integrating, 1 is x, 2e to the power of negative x is negative 2e to the power of negative x, and e to the power of x is e to the power of x. Substituting the upper limits and the lower limits, we have, simplifying, we have ln 2 minus 1 minus 2 minus 0 minus 2 minus 1. Simplifying further, the area of the region is ln 2 units squared. In example 3, we are required to sketch the curve xy equals 6 and the straight line y equals 9 minus 3x. Hence, find the area bounded by the curve and the straight line. So the first step is to find the points of intersection between the curve and the straight line. This is done by substituting y equals 9 minus 3x into the equation xy equals 6. Thus, we have x multiplied by, in brackets, 9 minus 3x equals 6. Simplifying, factorizing, we have x equal 1 or x equal 2. When x is 1, y is 6. When x is 2, y is 3. Now, the curve xy equals 6, which is y equals 6 over x, is a reciprocal curve. So the shape of the curve is an arc. The asymptotes of the curve are x equals 0 and y equals 0. This means that the curve will never cut the x-axis or the y-axis. So now let's sketch the x-axis, the y-axis, the curve y equals 6 over x, followed by the straight line y equals 9 minus 3x. The straight line and the curve intersect at the point x equals 1, y equals 6, or x equals 2, y equals 3. Take note, the sketch is not drawn to scale. Hence, the area is given by the shaded region. The area of the shaded region is obtained by finding the area inside the outer curve, which is the straight line and has a shape of trapezium with width 1 unit, and the lengths of the parallel sides are 3 units and 6 units respectively. Thus, the area of the trapezium is half multiplied by the width, which is 1, multiplied by the sum of the parallel sides, which is 6 plus 3, minus the area inside the inner curve, which is the integral of 6 over x from x equals 1 to x equals 2. Simplifying and integrating, we have 9 over 2 minus 6 ln x from x equals 1 to x equals 2. Substituting the upper limits and the lower limits, thus the area of the shaded region is 9 over 2 minus 6 ln 2 units squared. We can also integrate the function 9 minus 3x to find the area inside the outer curve. Thus, the area of the shaded region is the area under the straight line, which is the integral of the function 9 minus 3x from x equals 1 to x equals 2, minus the area inside the inner curve, which is the integral of the function 6 over x from x equals 1 to x equals 2. Integrating, 9 minus 3x is 9x minus 3x squared over 2, minus the integral of 6 over x is 6 ln x. Substituting the upper limit and the lower limits, the area of the shaded region is 9 over 2 minus 6 ln 2 units squared. Or we can find the area by integrating with respect to y. That is, the area inside the outer curve, which is the straight line, and has a shape of trapezium, but with width of 3 units, and the length of the parallel sides are 1 unit and 2 units respectively. Thus, the area of the trapezium is half times the width, which is 3, times the sum of the parallel sides, 1 plus 2, minus the integral of the function 6 over y with respect to y from y equals 3 to y equals 6, which is the area inside the inner curve. Simplifying and integrating, we have 9 over 2 minus 6 ln y from y equals 3 to y equals 6. Substituting the upper limits, we have ln 6, minus substituting the lower limits, we have ln 3. Now we can simplify ln 6 minus ln 3 by applying the laws of logarithm for quotient, which is ln 6 over 3 is ln 2. Thus, the area of the region is 9 over 2 minus 6 ln 2 units squared. We can also integrate the function x equals 3 minus y over 3 to find the area inside the outer curve, which is the integral of the function 3 minus y over 3 with respect to y from y equal 3 to y equal 6 minus the area inside the inner curve, which is the integral of the function 6 over y with respect to y from y equal 3 to y equal 6. Integrating, substituting the upper limits and the lower limits, apply the laws of logarithm of quotient. Thus, the area of the region is 9 over 2 minus 6 ln 2 units squared. Since there are many methods that you can apply to calculate the area of the regions, so my advice is to choose the method that you are most comfortable with. Example 4. We have done this example in the previous lesson, area of region part 1. Here we are going to solve by integrating with respect to y. But first, let us sketch the curve y equal ln x minus 2, the straight line x equal 4, and sheet the region that is bounded by the curve, the straight line, and the x-axis. Then find the value of y when x equal 4. When x equal 4, y is ln 2. Next, we convert x in terms of y from y equal ln in brackets x minus 2. Thus, we have x minus 2 equal e to the power of y. Therefore, x equal e to the power of y plus 2. To find the area of the shaded region, we find the area inside the outer curve, which is the straight line x equal 4, minus the area inside the inner curve, which is the curve x equal e to the power of y plus 2. Simplifying, integrating, we have 2y minus e to the power of y from y equals 0 to y equal ln 2. Substituting the upper limits, we have 2 ln 2 minus e ln 2 minus, substituting y equal 0, we have 0 minus e to the power of 0. Thus, the area of the shaded region is 2 ln 2 minus 1 units squared. We can also find the area of the shaded region by finding the area inside the outer curve using area of rectangle. 4 times ln 2 minus the area inside the inner curve, which is x equal e to the power of y plus 2. Simplifying and integrating, we have 4 ln 2 minus e to the power of y plus 2y from y equals 0 to y equal ln 2. Substituting the upper limits ln 2, substituting the lower limits 0, simplifying. Thus, the area of the shaded region is 2 ln 2 minus 1 units squared. Example 5. Diagram below shows the curve xy squared equal 8, the straight line y equal x, and y equal 4. We are required to find the area of the shaded region. The first step is to find the point of intersection between the straight line y equal x and the curve xy squared equal 8. This is done by substituting x equal y into the equation xy squared equal 8. Thus, we have y cubed equal 8, y is 2. When y is 2, x is 2. Now, there are cases that we need to add to determine the area of the region. Refer to the diagram. The region can be divided into two parts. A1, the area that is bounded by the straight line y equal x, y equal 2, and the y-axis. Observe that the region is a right angle triangle. A2, the area bounded by the straight line y equal 2, the curve xy squared equal 8, y equal 4, and the y-axis. Thus, the area of the region is the sum of A1 and A2. Now, A1 is a right angle triangle, so area of the right angle triangle is half time base times height plus A2, the integral of 8 over y squared with respect to y from y equal 2 to y equal 4. Simplifying, integrating, substituting the upper limits and the lower limits, the area of the region is 4 units squared. Summary for today's lesson. First, if we have two curves intersect at x equal a and x equal b, then the area of A is obtained by finding the integral of f of x minus g of x from x equal a to x equal b. And if we have two curves intersect at y equal a and y equal b, then the area of A can be obtained by finding the integral of fy minus gy from y equal a to y equal b. And please take note, sometimes we need to add to find the area of the region. Okay students, that's about all for today. I end my lesson with a saying, practice makes perfect. Please do visit my channel, Cikgu Zana channel, for more video lessons. Till then, study well, stay safe, and see you again in my next video.